So 5 to 80. So this is hundreds of crores we are spending. So in that way, it is very costly also. Fourth one is very important, and it is very accurate. Requirement is very, very accurate. If you are talking about docking or the landing or pinpoint landing on ground. So like that, many things if you are talking, it is very, very precise. So the each system should behave to that accuracy. Higher accuracy, highest accuracy requirements are there, but this is very important thing compared to normal system to the space system is it is moving in a very fast rate, because fast rate it has to be accurate at fast rate. That means the spacecraft, when it is something on 10 to 11 kilometers per second, it is moving. So now we are assessing the accuracy every milliseconds, in 20 milliseconds or 10 milliseconds or 5 milliseconds. So it has to be accurate at a faster rate. But here in ground, it is not so. Ground, it is not that. We need not perform in microseconds and nanoseconds or the milliseconds. We are having sufficient time to do things. But in space, it is not so. So precision and perfection at every mission is important. This is the thing. So space systems are very, what is called little, in the sense when you are talking about accuracy or the performance you are talking, it is much what is called a bigger perspective. We have to see that. So next you see the next slide. And one more thing is very important, because the space systems have to behave in orbit at the extreme environments. These are all the extreme thermal, mechanical, vacuum environment. If you are seeing, that is the bottom I have written, no, International Space Station, the temperature outside is, when it is, sometime it is 121 degree positive, sometimes it will be minus 157 degree negative. And at deep space, when you are going for deep space mission for Mars and all other things we are going, it is going to minus 270 degree. I mean, some of the system has to work in very low temperature also, even though we are giving some heaters and all we are providing to maintain the temperature, but it is sometimes it will be exposed to the extreme environments. Here in ground, worst case environment will be minus 50 degree in Russia, but when space it is going more or less minus 100 degrees, a nominal number it is. And during what is called the mechanical means, now normally here in ground and all, shock level is very less. During shock or missile and any other applications, the shock is very, very high, and it is extremely vacuum condition it has to work. Vacuum is, you know, that in ground, let us say in atmosphere 101 kilopascal is there, there it is going to minus 5, minus 6, like that it is going. So minus 12 also it is there. So that extreme environment it has to behave. That is the important thing. And the radiation is there, high energy radiations are coming, ionizing, non-ionizing also. In that also it has to work. Microgravity environment is there, because in orbit when you are going, the gravity is less. So in that condition it has to work. Micrometeor and orbital debris. Now the major threat to space system is the orbital debris. In that also it has to escape and it has to work. So space environment is very harsh compared to the normal ground environment or normal known environment to the what is called the manufacturers or others. Space people will know that these are all the environment. It has to behave. The system has to be what is called the robust enough to perform in these environments. Next we go. So now if you see that, just you take this particular the slide. Now this is just a failure, because recent one from the report, one report I have taken. If you are taking a spacecraft, let's say if you are seeing, then in a spacecraft, these are the common elements. The structure is there. EPS is the electric propulsion. Propulsion is there. Structure is there. Propulsion is there. Communication is there. Computers, onboard computers is there. OBC, onboard computers is there. Power generation, solar cells are there. Transceivers are there. Then for ADCS, this attitude determination and control system is there. And payloads are there. These are all the major elements in a spacecraft. Similar thing only it is there in the launch vehicle also. It is having a navigation guidance control. It is equivalent to ADACS, and the structure is there. Payload is there. The what is called antennas will be there. Computers will be there. Solar cells alone will not be there. Transceivers will be there. So this more or less all the elements are available in a different what is called the different way it is there. So these failures, if you just see the mid of the top, if you are taking the launch failures in past 15 years that when it is analyzed, if you are seeing that these are all the percentages where and all it has failed. If you see propulsion failure is 54%. Our topic of interest now today, if you are seeing that the trajectory and attitude control system, it is something around 18% it is there. Sorry, something around 18% is there for the launch vehicle. The right hand side, if you see the spacecraft failures. Spacecraft failures also, the payload failures are there. Then the TCS. There, if you are seeing that something around some 1%, 15% will be their computers and other things. So now the failure when they are analyzing, because now what I wanted to tell is almost all components are prone to failures in space, not that one specific component alone. All components in all subsystems in all systems in the spacecraft or launch vehicles are prone to failures. And the failure modes, if you are seeing that some of the designs, some of the parts and materials, some are operational mistake what we are doing. Workmanship means instead of connecting one way, another way of connecting things. It will be coming out at later stage. Software failure is a huge failure actually, that is there. So now if you just see from this picture, this slide, you will be understanding that space system, almost all components are prone to failure. Even after testing in ground also it is failing. That means it is when the extreme environment is behaving not normal. So these are all we have to take care in the thing. So how to reduce these failure rates? These are all because people are losing a lot of money. Now it is becoming a debris in space. That is the most dangerous thing, not money alone. It is a threat to everybody. So failure for space system is not allowed for the future generation, because this, if it is becoming more and more debris, launch will become very, very tough. That is why. So failure should be totally avoided. It has to perform. When it is performing, it has to perform for, because there is another part also, within how many days it is failing, like that and all it is there. That slide I have not taken. But if you are taking that way, it has to perform till the what is called allotted time or the intended time. So failure for spacecraft is a major threat to the what is called a generation to come. So that is why we have to be very, very careful. So now you go to the next thing. So now if you just see that now, so functionality of a space system, if you are taking now from the space system, what I meant is actually now if you see launch vehicles and the spacecraft launch, I mean launch vehicle launchers, like that if you are taking launch and the spacecraft. So now launcher, the major thing is injecting the spacecraft in an orbit, intended orbit, orienting the spacecraft, that is another thing. Maintaining the space probe in Earth or other orbits for performing intended function for that duration. This is the left side thing I have put it. Right hand side, if you are seeing, because left side and right hand side, there is a small difference, because I will cover it later, because when this is actually in orbits or in orbits, things are happening from the ground to orbit. Right hand side, if you are seeing that from the orbit, or it is coming back to the ground or another object, it is landing on another object. That is a relative what is called motion between the things are there. Here it is not so, left side it is not so. From the ground it is lifted, it will be injected or put it in some orbit and maintained in that orbit. There is nothing to what is compare the performance with respect to another one, because it is going to hit like that. Right hand side is not like that. It has to be compared to when something is coming to the ground, up to the surface, what distance it is or what speed it is, when it will land and when it will touch, at what speed it will touch, with respect to some other thing. So if you take bottommost, it is a docking. Docking, if you are seeing that between two things it has to happen, both are moving. So with respect to another, we have to check. So pinpoint landing is there just prior to that. Right hand side, if you are seeing that on the meteoroid, means this something is landing. So that is also there. Then first one is the Chandrayaan lander. So pinpoint landing and docking, for that, this is another way of space system. So left side, this next for subsequent slides, this what is called, why this slide is coming, that we will come to next. So if you are going for a function of a launch vehicle per se, launch vehicle, if you are taking it. So launch vehicle is a multi-stage rocket. What it does, it is, you know that PSLV, GSLV, you must have seen all these things. So launch vehicle, a multi-stage rocket injects satellites after following a predefined trajectory. This This trajectory is already defined. This in that defined trajectory, this has to move. At an altitude means up to what height it has to reach, with the velocity, at what velocity we have to inject, at what orientation of the spacecraft it has to be there at that point of injecting. So this is what the all along with respect to the launch vehicle. Left side, if you are seeing that at what time, what stage, up to what stage it is performing, what are the functions happening in the left side. And at each time, what is the velocity, what is called relative velocity with the range, altitude, all other things are given. Then this is okay. The other thing is from the ground trace, how it is coming from the launch pad to the what is called other orbits. That is what given, right? Rightmost side is the what is called. Finally, they will declare that what is the orbital parameter. Orbital parameters, what is the perigee, what is the apogee, and what is the inclination of the particular the orbit inclination. For the what is called the polar orbit, it will be 90 degree. Other geostationary orbit, some other angle. So that you can see that 0 degree, it will be there. Bottom, if you are seeing, right hand side bottom, if you are seeing PSLV, how the track will be there from the Earth, India, the launch pad, how it is moving. The launch vehicle is moving from the what is called the for GSLV, for the geosynchronous orbit spacecraft, how it is moving that way. That way you can see that. So this is a trace. Next, the function of a launch vehicle is to inject an object, that is inject a spacecraft into the intended orbit at particular altitude, particular velocity, particular orientation. That way. Next. So in that, how we are, what is called, what we are doing, the intended orbit, in a predefined trajectory, it is told, no? In that trajectory, what we are defining, if you are defining, first we have to know at what point, where am I? And what is my speed and the direction, where I am pointing. This is what it is required. Then what is the thing is the guidance. Guidance not to get from one place to where I have to go, in which direction, at each point, what is the velocity, what is the thrust I have to perform. So that is a guidance. Fourth one is means there are thrusters. That is the propulsion system is there, or thrusters are there. How to control to achieve this orbit. So there are three things actually. One is a predefined orbit, it is defined and it is in the guidance profile. Navigation systems will tell that where I am now, at what point I am orienting, like that it will tell navigation. Control will tell that, means we have since to follow that trajectory, means the how to, means whether I have to give this thrust more or less, or orientation I have to change or less, all the things are done by controls. Control with the propulsion, and there some actuators will be there. With that actuator, they will control the directions also. So now if you see bottom, if you are seeing, this is the trajectory done by guidance, it is trajectory optimization. Reference is there, desired position and desired altitude is there. This is our reference. Then control is done by the what is called our actuators. This is a plant. Plant is the what is called the launch vehicle. Launch vehicle per se is a plant. Navigation is a sensor and algorithm. So now if you see for achieving a thing, guidance, control and navigations are worked together. This total segment, guidance, navigation, control in a launch vehicle is a crucial part. It is a part of the avionics system in a launch vehicle. This slide, this you'll be able to just overall, you must have got it. So navigation will tell where am I, at what speed I am there, what orientation I am there, like that it will tell. So guidance, it will be guidance control is next function to make the launch vehicle or any thing in particular desired thing or intended trajectory. So next slide again. So if you are taking, that is the other one. That is, what we are defining for launch vehicle is the what is called perigee, apogee, and inclination and altitude. All these things we are means perigee, apogee, like that we are telling. For a spacecraft, if you are taking that, spacecraft specification normally will tell that Earth observation satellite, it is at what altitude it is there, what inclination it is there, what is the period, means orbital period, what is that. So revisit capability and all, that and all depends on same orbit, same time when it will come, mission life, payload, that resolution, these are all the instrument, what is the thing. So there is one attitude and orbit control is that it's a 3-axis body stabilized. That means its attitude and orbit also we have to control on the way, because for the 7 years life, we have to continue to correct the attitude. Attitude means orientation of the spacecraft with respect to the reference. Means fourth day, it has the same point, it has to come, means it has to be oriented in a particular way. So this orientation means orientation of the spacecraft. And the orbit control, that is orbit raising, all the things, a small adjustment they will be doing that. So on three axes it will be stabilized using some actuators. In the launch vehicle, you are seeing that the actuator is mainly the propulsion system and the other ones. Now here, if you are seeing the reaction wheels, torques, electric propulsion, those are all things will be the actuators. Next one you go. So because there we have seen that, because we are going to talk further the navigation. So there in the launch vehicle, we are seeing guidance, control, navigation. These are all put together. It is doing that function of a launch vehicle. Here we are calling AOCS or attitude, ADCS. Attitude, determination and control system. This is ADCS is the part in the spacecraft. What it does is initial orbit is given by the what is called the launch vehicle. Initial rate and orientation also will be given. Then from there now, achieve and maintain required orientation. If you see the bottom left, if you are seeing immediately after, it is in the folded way only it will be there. Now, when it is coming out, then we have to, what is called the solar array has to be deployed. Then it has to be put in particular orientation with respect to sun. So this solar panel deployment and orientation, then when the payload is operational, payload will be which direction, and accordingly the what is called the orientation will be changed. So achieve and maintain required orientation for a power generation, payload operations and orbit control operations. This for this one only, their guidance navigation control equivalent to that. Here attitude, determination and controls. This is there. So provide interface to the achieve desired orbit, provision for correcting the perturbation. That's what I do. So need for attitude control. Point solar panel to sun to generate power. Point antenna towards earth for proper communication. Point payload cameras towards target for imaging. Orient thrusters for orbit maneuvering. That means rising or orientation change, all of things. Control heat dissipation. If when it is something is always pointing the earth, means the sun, it will be getting heated up. Some areas to be slightly rotated. That thermal control they will do. Avoid damage sensitive components. When it is something is going to hit, you have to move it also. That one only this is performing. So you keep in mind, attitude control systems needs sensors. Guidance navigation controls needs sensors. That functions navigations here also equivalent to navigations. Next slide. So now we are coming to navigation. So we have talked about the guidance navigation control, or means functionality of launch vehicles, spacecrafts, requirement of the what is called the guidance and control for that sensors. So now we will come back to navigation. Next is a navigation. So navigation is the determination of a physical body's position and velocity related to a known reference. So normally we will be calling Earth reference, Earth center as a reference. So navigation is the determination of physical body's position, velocity. So position and the velocity in the course of movement, where am I and where I want to be. This is what the navigation meaning of that. The forms of navigation, we know that there are so many forms. Visual piloting, that's what we are normally doing, seeing the landmarks when you are moving further. How we are doing visual piloting, we are doing. So next is the dead reckoning. Dead reckoning bottom I have written, the process of calculating one's position, especially at sea or any other place, by estimating the direction and the distance traveled rather than by using landmarks and astronomical observation. It is wherever we are not able to see landmarks and the what is called some other celestial objects. Now we are depending on the what is called a direction sensing equipments and the distance traveling, means how much distance traveled to measure that, and the time. Three things only we are depending. So this sensor dependent items, dead reckoning. In that one only, another thing is coming, inertial navigation. Inertial navigation we will come to next. So in the broad classification of avionics, under guidance and navigation controls, under navigation, the inertial navigation is coming. So celestial navigation uses with respect to star and other one. Electronics navigation, mainly GPS and other ones. Next slide. So inertial navigation. Now inertial navigation we are coming. Inertial navigation being inertial using a sensors which is based on the what is called principle of inertia. Inertial. So inertial frame means it is non-moving, non-accelerating, non-rotating with respect to fixed star. This is one reference point, reference frame that is called inertial reference frame. Inertial, under using this inertial reference, mostly the Newton's laws of mechanics, whichever is used, means whichever is obeying, that one only is used actually. So accelerometers and gyroscopes are as inertial sensors. So that now you know that accelerometer, if you are integrating 2 times, we will get the position. How we are getting the position? Anyway, these are all things will come next also. So now on the right hand side, if you are seeing, we are having in all 3 axes, accelerometers and gyroscopes. Use gyros. Gyros are for the orientation, a rate to measure the angular motion. Angular motion means rotation. From where its attitude related to navigation reference frame is derived. That means attitude is the orientation. Orientation means about a fixed point, it is rotation, 3 axis rotations. Measure specific folds using accelerometer. That is a linear motions. Now, that is accelerometers it will do. Gyros will do the orientation, means the directions. Acceleration will give a velocity direction. Velocity along that direction. Resolve the specific folds into navigation frame of reference using an attitude information. Attitude is the gyro information. Integrate acceleration to obtain velocity and the position. Use initial condition at start point. What is what? What is your start point of the x0 or what is the start point of the vx0? This is what ax only we are measuring, and the time also we are known. We are known that the x0 should be known to us. Initial velocity, initial position is should be known. Then from there, what is called orientation also to be known. Then the acceleration we have to measure it with the accelerometer. When we are integrating. Then we will be able to do current positions. We will be able to see. This is inertial navigation, or the basic principle. So inertial navigation uses sensors, accelerometers, and gyroscopes. This you keep in mind. Next. So now component of navigation systems. Now if you see right hand side, components we are taking 3 gyros for 3 directions, 3 accelerometers along that directions, measuring the linear thing, and the one is rotation. Then right hand side, they are putting that compute attitude vector, attitude orientation. Then axis and accelerometers, that now from the orientation of the axis, we'll come to know what is each accelerometer behaving which axis. Now, then from there, all these algorithms will be there to find out positions and velocity. So now to find that, now there should be a sensor. That is what IMU, inertial measurement unit. A navigation system consists of a measurement unit, then support electronics, then converting this what is called frame of reference. With respect to frame of reference, what is the attitude and the velocity and the position, to that computers, navigation computers are used. So this put together the navigation, what is called the system, inertial navigation system. Left side, if you are seeing bottom, it's an IMU. IMU consists of accelerometer and gyroscopes. Navigation computer for the what is called from the measured values, how we are converting into the speed, distance, and heading angle. Next slide. So now each launch vehicle will have one what is called the inertial navigation system launch vehicles. Now it will be there in the avionics bay, upper bay. Then Delta Ariane 5, Delta 4, and PSLE, GSLE. These are all the launch vehicles. For that, what are the type of what is called the inertial navigation systems are used. Right hand side, if you see the spacecraft things. Spacecraft now, MAVAN is the Mars orbiter thing, equivalent to. Then Cassini, this that is the what is called the Saturn mission, that one. Then right hand side is the Chandrayaan 2, 3 like that. So this there we are using these bottom things are the IMUs of what is called IMU and INS of the what is called the this spacecrafts. So for the launch vehicles and spacecraft, just to tell them this package per se will be available in the inside the avionics bay. Next. So now you just come, that is what it does. Then all the functionality we understand. Then how the error goes, because now we have to tell that what is the accuracy of the system. So why it is so critical, that accuracy how we are defining. So now just see, before that, you just left side, you just see how it's a nomenclature of this particular INS. We will just note that range is actually now what is called the how much maximum what is called the acceleration or the rate we can measure. these are all mentioned by G. G is 9.88 meter per second square. You know that G. Degree per second is the rate. So rate degree per second. Other one is the G. This is what the what is called acceleration, and the gyro means rate range or nomenclature. Then next one it is coming, because now if you are giving input output characteristics, if you are drawing, you will be having a straight line, and there will be some portion, it will be a bias will be there. So that mx plus C, that we call as a bias. The bias should be, because in G, when you are talking for accelerometer, it has to be in milli Gs or micro Gs. That is what 10 power minus 3 or 10 power minus 6 G. That C part. And for gyro, we are calling as degree per hour, not for degree per second, degree per hour. Now, if you take that, roughly I will tell, for range, 60 G is the what is called a range. And the gyro, if you are taking for different purposes, if you are taking for spacecraft, it will be less, 10 degree per second or 30 degree per second is sufficient. But for the what is called aircraft or launch vehicles or the missiles, it will be 400 degree per second, it will be there. But in the bias, if you are talking, this is in degree per hour. That means that degree per second divided by 3600, you have to put it. So degree per hour, that will come back now later. Bias repeatability. Once if you are measuring, you are calibrating this sensor for the input and output. Then you will be estimating the C. This C, that is the bias, how it is repeatable, whether it is stable or not. That also we will be putting that error in the estimation, or its repeatability or the stability of that particular number. So that we will be defining in milliGs. Then bias error over temperature. If your temperature excursion is there, let us say 0 to 70 degree or minus 55 to 70 degree, it will be varying with respect to what is the temperature. So millig or micro G by degree centigrade it will come. There will degree per hour per C, temperature will be there. Scale factor, that's slope. Slope only we are calling as a scale factor. The scale factor is a, let us say it's a, there if you are talking about scale factor, it will be non-linearity, one term will be there, second order or third order non-linearity. And error, now because once if you are estimating the scale factor, now that is a accelerometer, if you are talking the force rebalance accelerometer, milliampere per G. Now this is actually gyro, if you are taking volts per degree per second, like that if it is there, that volts whatever we are measuring, whether it is stable or not, that slope, how far it is stable, that we are calling as ppm, part per million. So 1 degree per second, if your rate is given, if it is 100, what is called the ppm means 100 into 10 power minus 6 degree per second is the error. That way. So this is what the error terms it is coming. Then misalignment. Misalignment is means with respect to that also a slope means from the what is called, that is embedded into the bias if you are mounting in a fixed thing. Misalignment. From the input axis. From the input axis, how the what is called measured axis is tilted. So now if you see that how it is progressing with respect to time, because everything we are doing with respect to integration with respect to time. That is what very important here. So time, now short term, because when it is in an orbit or during the flight, let us say, if you are taking that in a flight, in a spacecraft, let us say, when it is moving, it is in a constant speed only, it is moving, let us say. At that particular point, what is the error? Position error it is coming. It is an initial position error, that is we have seen that. Velocity error. Now that is acceleration, velocity into t is the position. So velocity into t, right hand slope if you are taking, when t is increasing, if there is an error in the velocity, it will be linearly, it is increasing. It will be increasing. Leveling error if you are taking, that is misalignment. Misalignment if error is there, some angle error is there, that how it will be contributing with respect to time. It will be going in a what is called square effect. Accelerometer bias if you are taking, let us say 100 micro G is my bias stability. If I am talking 100 into 10 power minus 6 G, that is my bias stability, let us say, if I am putting. That thing will be, if you are acquiring for long time, then it will be going in a time t square effect will be there. That t square if you are taking, how the error is building up to, with respect to acceleration error, rightmost bottom it is there, with respect to acceleration error, that is what accelerometer bias, that when it is changing, how it is varying with respect to time. If angular rate, some error is there, drift rate, no, here it is put bias in the angular thing, the gyro bias, how it is varying with respect to 3 And attitude error, fixed attitude error, how it is changing. So with respect to time, this error is increasing very large. That is why now if your sensor is working well for a short duration, then it is okay. If it is required to work for long duration within accuracy, that means your error terms, that is bias stability or bias repeatability or scale factor error should be very, very less. So now we'll come back to the next slide you go. So now if you see, people have graded this particular thing with the what is called if tactical grade. It's a missiles and the other one. Tactical grade, navigation grade means for the spacecraft and the what is called the launch vehicles, aircraft, like that and all. It's a navigation grade. Now initial position error, if it is like this, let us say there, you just put it initial position error, initial velocity error, initial roll pitch error, accelerometer bias error, gyro bias error. If you are taking that for a tactical grade, 300-second time, if you start to end 300-second, if you are taking tactical grade sensor, error will be 2.5 kilometers. With this tactical grade is what? You just see the right hand side. Tactical grade, what they are calling is the error is 1 degree per hour is accepted. And that's what they have mentioned there actually. And the 1 millig is your bias, that is also accepted. Even 10 degree per hour is also accepted for a tactical grade. 1 to 10 degree per hour you can take it. So tactical grade, accelerometer and bias error if you are taking, gyro bias bottommost diagonal 10 degree per hour, and accelerometer bias is 1 millig, that is 1000 microg. If you are taking, that error goes within 300 seconds, you will be having an error of 2.5 kilometer error. When a launch means in the launch pad, if you are launching with 300 after 300 seconds, if there is not much what is called G, that is scale factor is very large change is not there. Then because of the bias alone, bias stability alone, the error is coming 2.5 kilometers error will come up to 3. When that missile is traveling for 300 seconds, then error will be around 2.5 kilometers. But it's the same thing if you are taking a navigation grade sensor, which is 100 microg, that is 0.1 millig, and 0.01 degree per hour. If you are taking that, error goes to only 70 meters. That means for the same 300 seconds. Because for a longer flight, this 1 hour flight from Bangalore to Toronto, if you are taking, there is no other aiding elements are there. Errors will be that is 1 nautical mile per hour. That's what they have given. No, you are seeing that categorization right hand side. If you are seeing 1 nautical mile per hour means per hour, the error will be 1 nautical mile, roughly 1.8 kilometers it will be coming. That is the error. So we are what is called correcting with respect to other sensors and all, but still I'm just 1 nautical mile per hour if you want for a navigation grade thing. So 50 microg and 0.01 degree per hour. If you are going for a submarines, one day, one full day, if it is 1 nautical mile per hour only, I should get it means we have to have an error of 0.005 degree per hour in the gyro, and the accelerometer bias should be 0.03, that is 30 microg. That means what it comes out is now, if you want to have then even though what is called higher accuracy systems for a deep space missions and the submarines like that thing, the sensor accuracy should be very, very high. That means accuracy, what we are calling in terms of bias and its stability. So accelerometer bias and gyro bias should be very, very low. That is the better performance. Then we'll be getting error will be less. The navigation grade for aircraft and other spacecrafts also, 1 nautical mile per hour class means 0.01 degree per hour. So for space systems, deep space missions or a launch vehicles, other one, it is mainly navigation grade and military grade only we are talking. So that means we have to have a sensor for a performance of 0.01 degree per hour and 0.005 degree per hour or 50 microg to 30 microg, even 100 microg, that range only. If you are taking, we are talking many things on the cell phones and other ones and all. We have come across what is called the IMUs and the accelerometers in our cell phones also. Those things are in milligis, not in what is called, not even 1 millig. It is very high milligis and degree per second accuracy. We cannot compare these two things for the performances. Now you go to the next one. Next, we have to see that how we are achieving this sensor, how we are achieving this type of performance. To achieve that, what we have to do. This is now on the inertial sensors we will talk. Then what are the deciding parameters? We'll just check it. So the leftmost corner, the side I have given the spring mass system. It is for accelerometers. And then the next one is the what is called gyroscope principle, conservation of angular momentum. Third one is the path length difference when in a rotating what is interferometer, active interferometer. This is the ring laser gyros. This one. Last one is the Coriolis vibratory accelerometer gyroscope, that what we are seeing in IMU in the MEMS gyroscopes in our cell phones and all the other ones. No, the drones like that things and that. Okay, now next thing. What is these are all the various principles. Just put it in the slide. Next thing. So next, now in a little okay overall explicit manner we have put it. There are gyros and accelerometers working in different principles: optical, vibratory, and mechanical. Mechanical things are very old. Then optical gyros were there. Then vibratory gyroscopes came. That next some subsequent slides it will be covered. This slide will tell the overall summary of what type of principal technologies are used for gyros and accelerometers, and what are the type of this ring laser gyro. Like why for our discussion I am taking ring laser gyro and the quartz flexure accelerometer. Why it is taken is particularly these are all these two sensors, particularly quartz accelerometers and the ring laser gyro. Last 60 years. What is called last 50 years, roughly over 50 years, it is no competition is there for this in this particular gyroscope. That means it is performing last 50 years in the navigation area. That means that much matured and that much accurate sensors, and it performs to the lowest level to the highest level. The ring laser gyro, it is simultaneously 400 degrees per second also. Range you will get same way. Resolution also will get a better one. But a quartz flexure accelerometer also like that. 60G range will be there. In 1 micro G resolution you will get. None of other right hand side accelerometers, silicon accelerometer, it has come. I will go through next slides. And other sensors have not come to up to that stage, covering entire spectrum of these space vehicles, in the launch vehicle, missiles, the drones, or the what is called the submarines, or the all the defense and the space sectors. So now right hand side, now quartz pendulous accelerometer we will be discussing on the top. At that time we will cover some point on silicon MEMS accelerometer also. Vibrating accelerometer we will not cover, but this principle I will tell later. It's a resonant accelerometer. Gyroscopes, mechanical gyroscopes I will not cover. That is mainly the principle of angular conservation of angular momentum only. It will be taken. That will, if time there, we will go to that. Next slide you go. So now this accelerometer, different companies name only. Now we will not dwell here because the time is not there. We'll go there next. Next you go. So now the accelerometer basic is we know straight away a single the spring mass system, right? The picture you see that the mass is hung on a spring. And then there is a damping for the what is called the if a jerk comes, how it is behaving. Mx double dot plus cx plus what is k. That one only. Now a mass is there, a spring is there. When an acceleration is given, the mass will deflect. Means then the because of the spring, m into g will act on the what is called hung mass, and it will displace. That displacement left side is measured with respect to the frame. Now you see that the this is the left hand side. If you are seeing now, f is equal to m into a, m into g, a is equal to f by m. Force whatever we are giving. How to measure the force? Force now we are converting force into k. Force is equal to this whatever force acting on that, it is translated to the displacement with the spring constant of the material. So f is equal to kx. When you are measuring the deflection, it is proportional to now a. This is what the method of measuring this inertial force, inertia force. Deflects a spring and measure its deflection. This is a pendulous accelerometer principle. Now to determine velocity, v is equal to u plus at. This is already covered. Now you just see left side to right hand side how the spring now instead of keeping the spring mass system, now we have this spring means it should not resist anything. Whatever input is given, it has to deflect the what is called the mass. So now this spring we are converting into a hinge or a flexure. Flexure is a thin member, elastic member. Any force is given, the force acting on the mass, which is the right hand side, will be deflected by the what is called flexure. It will be allowed to move, allowed to rotate. Now here left side is the translation motion, right hand side is the rotation. rotational means the twisting thing, torsional motion. Now, if you see that, and then the deflection, the what is called the blue color block, how it is deflecting, that because of the G, the deflection to measure that we are having a pick-off. Pick-off is for measuring the deflection. Then if you want to work in a closed loop, it is to bring back in a null position, that force for rebalancing, the rebalance force measurement will give the what is called whatever G input. That will cover it next slide you go. So now if you see further, now this is left side we already talked. Now we have seen that previous slide, we have seen mx double dot, because now here we are converting into the moment of inertia and the damping, then the stiffness in angular terms, in radian terms actually. Now then accelerometer needs, one is called basic elements of accelerometer if you are talking, a mass which is called a proof mass. A mass is there, the blue color thing. A suspension which locate the mass, that is what the flexure or the hinge. Left side you are seeing that. A pickup which puts out the signal related to acceleration, deflection measurement. A force designed to oppose the inertia force. When a force is given, it will deflect down, but a equal and opposite force will be given back to pull it to the normal position. That is what the force it does. That we will see next one. So right hand side also, if you are seeing that, when it is coming, it's a pendulosity, not that mg alone we will talk. We will talk at what distance from the what is called deflection happens. At a left more distance, center of gravity of the proof mass and the flexure, lengthy flexure if you are having. At the start point only it is deflecting. Then it is giving a what is called a angular deflection. That is what? That is given by a torque. That is what? Torque F into L. It is equal to mg into L. This P into A. This P is equal to ML is called pendulosity. Normally in accelerometer we will talk about pendulosity. Now bottom how it is done, the accelerometer performance if you take pendulosity, that is when G is acting on a proof mass, it is a pendulosity is acting. The pendulum, it is deflected, that is this particular, that is pendulum dynamics if you are taking that. This sensor that pick off it measures, then rebalance it is done by the amplifier, I mean electronics. The torque converter, that rebalanced torque converter is the left side. It will be always maintained in a null position. This anyway we will cover to the next one we go there. Again, we will come back to the means 2-3 slides, because this accelerometer, if you are taking it, many technologies are there, open loop or closed loop. When deflection alone we will measure, we will not rebalance it. Then our ranges will be coming down, because the deflection, when it is range and resolutions will come. If you want more range, resolution will come down. For the MEMS, range is sufficient, resolution is not required. For a spacecraft thing, range is also required, resolution is also required. Proof mass or the connecting part is flexure. Pick off electromagnetic measurement, we can do capacity measurement. Bottom is the piezo resistive measurement. Electromagnetic measurement is there, means the pick off is also there. Forcer is also electromagnetic is there. Right hand side you can see that. Bottom most is the electrostatic forcer and pick off also. Damping, gas damping like that. Okay, these are all we leave it. Next you go. So now accelerometer, if you are seeing how it is progressing, because 1960 onwards, it is pendulous accelerometer. Earlier, before the, initially it is a pendulous accelerometer with the fluid damping. Damping is done by the fluid. Now later it was, this one only, next one only we are going to discuss, mechanical pendulous accelerometer. Rebalance accelerometer, it is not a fluidic damping, it is air damping only. Next one is the vibrating beam accelerometer and MEMS accelerometer. It's a progression with respect to time. If you are taking mainly, the progression is coming because the number of components they want to reduce it, make it simple, and it's a solid state. Pendulous accelerometer fluidic is the n number of components are there, more than 100 components are there. When your component numbers comes down in the pendulous, next thing, air damping thing. Vibrating accelerometer, further it has come down. MEMS, it is very small packaging, very small, in milligram size only it is. So form factor and the producibility, sizing, complexity to reduce, but accuracy you improve that. That way only this progress has happened. Next. So now you just see how the accuracies are met by the different technologies. If you are taking that, gas damping accelerometer only we are going to talk, that is the pendulous accelerometer. Fluid gas, that covers even 5 micro G to 1000 means 100 micros, that range it is there. Wide range it is working. And scale factor, if you see, roughly 100 ppm is the class for the gas damping accelerometer. Fluid damping accelerometer is not that accurate compared to that. PIGA is another type of accelerometer that is very, very accurate. It is very old technology. Now it is not there. MEMS, if you see, it is not that accurate. Scale factor is in thousands of ppm and the bias is in milligauss actually. So next. So now we will just see that some of the specification of the accelerometers. If we just see range now if you are taking 60G is the range for the standard, industry standard performance specification is 60G. Next is what is the minimum number we can do. It's 1 micro-G we can resolve. Absolute bias means that C, mx plus C is C form. Scale factor, what is the slope? That is 1.2 milliampere per G. That is a typical thing. What is it? 1.2 milliampere, I will just tell you later. Axis misalignment is the base of the accelerometer with respect to the sensing axis. Then the bandwidth, okay, up to what frequency? It's a dynamics, not in the static condition. The static G, it's a dynamic vibration G is coming. Up to what frequency? It will be truthfully responding. That is what it is given. So first this many up to 9 is a design parameters. Design parameters only. Second one, if you see that that is what the stability parameters. Now this is what people are specifying for a short-term duration for 1 year. This is industry standard is 1 year specification they are giving. This is a number they are giving. This is mostly depending upon the processes. So stability parameters mostly depends on processes that will come back. Temperature sensitivity for the what is called bias and scale factor. It depends on both design and processes. Environment, anyway, it is a user environment. User, what is called application specific thing. Minus 55 to 85 is for military specification. Vibration, all other things are mostly military specification. Now, once again, this thing you correlate with the right answer. This already we talked just to show that bias stability number if you are putting that. And scale factor stability if you are putting that, misalignment error if you are putting that, what it will come. So this number is like this. This is a specification of QA 2000. This QA 2000, I will just a brief introduction I will give. This is a Honeywell sensor. Honeywell is a company. That sensor QA 2000 is the mid variant. QA 3000 is the highest end variant. But interestingly, this is using only one technology. It is a quartz flexure pendulous base that I will show you later. Quartz accelerometer itself, this is the specification. Next slide you go. Now just before that, I will just show you that is the acceleration what we are measuring in PSLV and all. Now you see that it is linearly, it is going up, ramp up. Suddenly it is falling down. No, this is the what is called there only jerks or the shocks will come. This time it can go sometimes very large amount also in the missiles and that will go very high. That is why the 60G is required. Otherwise, for a Gaganyaan application, 6G is more than sufficient. For launch vehicle, this is sufficient. For maybe around slightly more is required for the ICBM or the missile, fast missiles. But it will not go to 60G in the linear segment. In one instantaneous acceleration for a smaller duration during jerks or during the shock or during the stage separation, it can go to very high G or even orientation time also. So that time it's very small duration only. So this is up to 60G. Now this slide, it is up to 60G it has to work in my 1 micro-G resolution here in the left side. This is mainly launch vehicle side. Right hand side, if you see simultaneously, now their left side scale, if you are seeing 40 meter per second square, that is 40 divided by 10 if you are putting 4G, 4 to 5G only there. Right hand side, if you see in a Chandrayaan 3 or the Mars orbiter, each time we are raising the orbit. Now this orbit rising time, what is the G imparted to the what is called the spacecraft? If you are taking this 0.04, that means 40 milli-G only, 40 to 50 milli-G. So, or 4 to 5 milli-G only. G in G only we have given. So 40 to 50 milli-G only it is given. There it is left side, it is 4 to 5 milli-G. Here 40 milli-G, 40 to 50 milli-G only. That means this during this time acceleration sensor should be, range will be less, but the resolution accuracy should be very high. That's what just I have shown in left hand side, right hand side. Now next you go. So typical Honeywell accelerometer, if you see the left side, one thing is the feature they are putting. What are all things are there? Right hand side, if you see, now here one point only you keep in mind. Now you need not read all these things. What I wanted to tell here is, in a particular QA 2000 model itself, you are having 3 classification. You understand now? That is 10, 20, 30. If you are taking 10 will be the best class. Then worst class, 30 will be the best class. That is what this fourth row, if you are taking 1 year composite repeatability, 160 micro G, 220 micro G, 550 micro G. Now just remember that QA 2000 is only one design, but the right hand side, if you are coming, that one design, but 3 different design, one process. When we are making the sensor, it is coming 3 different quality only. In the sense, accuracy simultaneously, all sensors are not following one particular number, 160 alone. It is because that the process dependent changes is contributing this one. Next slide, you will understand that. You go to the next slide. Next slide, if you are understanding, the QA 2000 I compared with QA 1400. If you see, design is same. The design on 60G is the range, resolution, bias. If you take, everything is small only. Everything is almost matching. But the bias 1 year composite repeatability, what is the number you are taking? 1000. That means, now that's what I'm just telling. QA 1400 is little old. Then the QA 2000 is now just in between. Then QA 3000, the latest. If you are progressing that, you will see same technology, that is flexure element is same, quartz flexure is same, but the accuracy is improving. For a same process, different accuracies you are getting. So you keep in mind, design can be constant, but fabrication methodology, testing methodology, and how you are improving the process technologies will alter the what is called performance also. So here I wanted, that's what I told, design, processes, testing, put together only we will be able to get good what is called sensors. Anyway, next we will go. Then in this, I will tell the technologies what is there. Next, we go to that. And somebody has talked. What is that? Hello? Shall I go through now? Hello?
Kindly mute those.
Yeah, next, if you are seeing the accuracy, how we are getting it for a sensor. Now, because now we are talking about highest accuracy sensors, how we are achieving that. You just see that design for performance, design should be there. Configuration also matters. Configuration will come back going. And the selection of material selection is very, very important. We will just see later. I will show you. Fabrication technology. The fabrication technology should not introduce any stress, or over time, the stress what is built in the fabric due to fabrication should not relax. So that way, we'll go through these points in the later by pictures. So precision stress-free assembly process. Assembly time, we should not introduce any stresses. High accuracy electronics is required because the signals what we are going to get is very, very small. That anyway, I will show you. High degree of packaging is required. Characterization, detailed characterization to understand, compensate, and modeling things are required. All these things. This is the way only we are achieving the best performance. Now you just right hand side, you see industry standard Q-flex accelerometer and industry standard MEMS accelerometer. I will just cover it later for subsequent slide. If it is not covered, I will come back. Now next you go. Now you just see, this is what the previous slide you go, then I will just tell you. You keep in mind the previous slide. Now you just see right hand side, whatever we are talking, Q-flex accelerometer, QA 2000, 1400 or industry standard accelerometer. Now many people are working on this quartz flexure technology. The center, there is an element, no? Center, you are seeing that. This is the pendulum. Pendulum at the center. I will, next slide, you will be able to see that. There is a pendulum at the center. We'll go to the next slide. Then it will be easy to understand. This configuration to keep in mind. Okay, now leftmost corner, you just come and see the same thing, whatever we have told, only it is shown. or in between the center also see, or right hand side you see. There is a, now we know that there is a proof mass required. It should be hung in a, what is called the flexure of a flexure hinge or a spring. Now we are having in this particular configuration, a circular disc is there. It is machined in particular shape. And we are seeing that flexure, it is mentioned, a dual hinge, it is mentioned. No? This dual hinge is this particular portion alone, dual hinge portion alone, machined to very, very small thickness. Very, very small thickness. Right hand side, you see the pictures. Now, just to show you. Now, when you are seeing that, right hand side, the topmost, you are seeing a displacement due to the inertial force. Now we are having one horizontal pendulum. This horizontal pendulum, when G is given or an acceleration is given, how it is deflecting, it is there. Now that is what this put. That bottom thing is, now there are two surfaces they are showing. Now these two surfaces, the reference. Now you just come back to the leftmost corner, leftmost bottom corner. If you are seeing, there are two segments on that. One segment is on the top, one segment is at the bottom. In between, one right side, one disc, one plate like that, it is there. No, the plate. The plate is hung on a small, what is called a small element. It is the flexure element. It is there. No, that flexure is not mentioned in this. Now, then you are having a coil. A coil is bonded on a plate. This is what right hand side you are seeing. Now, the two coils are there, and there is a magnet on the top. On the magnet. So please go to the previous slide. I will just show you. Come previous slide. You go. Now you see that previous slide top. If you are seeing, there are two housing, top and bottom. You just see that in a bottom housing you are seeing in a magnet there. Top housing also similar magnet will be there. When this particular pendulum or the what is called proof mass assembly consists of one plate which is coated with capacitive pickup. We will see that later. Capacitive pickup, and there is a, this is for, that is plating is the pickup, whatever it is written is the gap. When this particular disc is sandwiched between this particular top and bottom magnet housing assembly. What is happening here, when it is all are clamped together, because of G, this will deflect. That the center portion along with the coil will deflect down. So when it is deflecting, a current through the coil is given. This coil, what is that? When the current through the coil will be intersecting a magnetic area, magnetic field. This magnetic field and current, that is F is equal to BIL, Lorentz force, will lift the pendulum. Because of the G, it is coming down, or and rebalance force is generated with respect to the deflection using a current through the coil and a permanent magnet. That means permanent magnet current torque. This is what it is happening. So that means there is a pickup which is coating. That coating I will show you later. And the coil is there. The flexures are there. There is a circular disc. This disc, two flexures are there. When G is there, it is deflecting down. When it deflects, then the pickup measures the deflection. It is giving a signal to feedback. A current is passed through the coil. The coil pulls back the pendulum to the null position. This is what it is happening. Next we come. So this is what, next slide. This is what explained in the right hand side. If you are telling top black two things, right hand side is a reference of the what is called the pickup references. When it is deflecting, the now we know the pickup is the capacity pickup. We know that epsilon A by D. D is the distance. When the distance decreases, capacitance increases. Other side of the pendulum also coating is there. So that deflection is more. So capacitance is coming down. So the differential capacitance is used for bringing back to the null position. Right hand side bottom, if you are seeing, that is what the rebalanced condition. It will be sitting in the horizontal position. When it is given a what is called the motion, that is sinusoid motion, if you are going, it will go up and down. The air will, inside the air, trapped air will be moving up and down, means sideways. That will provide the damping. So now you just see topmost, if you are seeing a pendulosity there is a pendulum. It's moment of inertia, a damping is there, and a spring constant is there. A pickoff is there, right hand side, KPO. A rebalance amplifier is there. So this is the resistance to what is called a torque, a current through the coil is flown to bring back to the null position. So current through the coil is the measure of the G. That is why milliampere per G. For a G input, this much milliampere is generated in the coil, means passed through the coil to rebalance. Next you go. So now you just see that these are all the things. Now this leftmost side, whatever you are seeing. So leftmost side, whatever you are seeing is the flexure pendulum. Now you are able to see, now there is a coating, a yellow color is there. That's a gold coating on the what is called pendulum. On the initial pendulum, there are two hinge, there are hinge axis there. Then there are two small bridges there. No? This bridge is the hinge. So now this is circular disc. This disc is that what I will just explain. Right answer. Now design guidelines. If higher the pendulosity, higher the scale factor, higher the sensitivity, higher the resolution. But large mass, that is the if you are increasing the mass, that is coil mass, if you are increasing, then also more deflection will come, more sensitivity will come. But this larger deflection and larger mass will create a stress on the flexure. So we cannot go for a large range. The range means range you cannot go. So there is a limitation. This has to be what is called done. Right hand side is the important part. A hinge. Hinge should be low rotational stiffness. That means any small, 1 micro G, even if you are giving also, this hinge allowed to move. Means it should not give a resistance. Must have high stiffness about the input axis and pendulous axis. It must not show torque hysteresis. This is what very, very important. Torque hysteresis means when we are multiple time, if you are putting on and off, or if you are putting a cyclic thing, when it is coming to rest, it has to come back to the same old position. That is what the bias repeatability is. So bias repeatability, the hinge material should be in such a way that it should not have any loss. That hysteresis loss should not be there. So we have to select material which is having a highest damping or lowest intrinsic, what is called loss. That means lowest intrinsic damping material we have to select. Then only we will get a law. Means even if you are giving multiple times put on, put off, or with respect to cyclic load if you are giving, then also it will come back to a good elastic material, equivalent to good elastic material, it will come back to the same position. So next you go. Next slide. So now this is what flexure material, that is the thin member should be a high Q material, very low hysteresis or very low damping should be there. So now you just have some numbers alone, we'll keep it here. Flexure's dimension will be told to 20 micron. Now this material, the total disc is then on that material is a fused quartz, fused silica or quartz material. Not a crystalline quartz, it's a fused quartz, amorphous material. This material only is used for these particular purposes. This member has to be 20, it's a glass, it is equivalent to glass. So it's a highly fragile material, but when you are making very thin and thin, if we are not breaking, it will work as a very high, what is called quality spring. So this is a findings actually, it's an innovation actually. That is why Honeywell is doing that business for a long, long time. So dual flexure will be there. Highest dynamic range is the range by resolution. That is this, if you see that per micro G, the deflection you have to measure is 5 Armstrong unit. 1 micro G is the resolution if you are talking, it has to measure with 5 Armstrong unit you have to measure. And if you are talking about the capacitance variation, if you are talking, it should be less than a 0.8 picofarad. So that is actually absolute capacitance is around 20 picofarad. You have to measure it in autofarad to compensate it. So next you go. So we will run through fast now. So these are all the, okay, when you are going for a sensor development, these are all the procedure we have to follow. But the major problem is actually this one sensor if you are taking, this sensor itself is the multiphysics, because mechanical is there, thermal is there, electromagnetic is there, electronics is there, then optics is there, everything is there. All type of materials in a single sensor it will be there. Machining methods are different. Mechanical machining is there, and the chemical machining is there. Like that, many things are there, and it has to be integrated very, very rigidly. It's not what is called change with respect to time. So solid state welding methods, diffusion bonding methods. I mean, these are all technology, high-end technologies are used for doing things. Next, you go. So now this is how we are testing it. Now you just will skip because we are having many more slides. Now go to that. And next, this is a testing how we are doing in the ground. Okay, next you go. So now one important part alone I will tell you. Because now if you are talking, now what we are calling as stability. Now if when the sensor is switched on in a normal condition, keep it in a stable position in a vertically up or vertically horizontal. Now you measure the output. The output for 5 hours, 4 hours, if you are continuously monitoring, left side, if you are seeing that, now left side, the output is very, very, very stable. Whatever bias is there, that bias is very stable. We are not giving any other input G. So at that condition, if you are seeing that output, you are seeing that standard deviation of the output, if you are taking 1 micro G. This is the best sensor if you are taking. Some sensors, if you are seeing right hand side how it is behaving, when you are putting on and after 3 hours, if you are taking the data, you just 4 5 hours, if you are taking, it is continuously trend. It is moving. That what is the meaning of that? Pendulum is continuously deflecting even without inputs. This is what the problem. Next thing is, next if you see, now it is so many days. One day we are calibrating, second day like that, we are subjecting to environments, thermal we are doing, vibration we are doing, shock we are doing, thermovacuum we are doing. After that we are coming back and testing. Good sensor, how it will behave. Whatever bias we are measuring, that bias will be maintained throughout the 4150 days of calibration. So that number is less than 50 micro-G, 100 micro-G, it will be there. This is what the finally 1 year stability and all we are talking about. This. Some sensors, what will happen after some environment, it will change or continuously it will trend. What is the meaning of that is, in a single switch on, without giving environment also, it is drifting. That is one short-term stability we are calling. After 1 day, nth day also, it is continuously changing. That is what we are calling as warm-up to warm-up repeatability. That is changing. So this is what the error, actually error in a sensor. This error is due to what? You just come to next listen. Now this is very small number. We are talking 1 micro-G is 1 Armstrong, equivalent in Armstrong unit we are talking. 13 micro-G our error means 1 sigma, that is a 3 sigma if you are taking, 45 micro-G is error means 40. Roughly 45 to 400 or 300 Armstrong unit only we are talking that. So this number, what it makes this number to change. Next you come. So now this is only to explain you how we are so critical, so delicate in this what is called space systems. Now you just see in the flexure we are having now, even though we are telling that this material is the highest quality material, it is not supposed to yield with respect to time or deflect with respect to time without loading that. So, but then on that material in the 20 micron to this area, we are going for a coating. Coating is done with the what is called gold and chromium. We are doing a coating. When we are coating it, now just to see that when it is going on the flexure, we are coating, then we are making the material on a fused quartz. We are having some other material deposited. The thickness is very, very small only, 3,000 Armstrong unit only. You know that 20 micron, 25 micron is your hair diameter, roughly. So now 3000 Armstrong unit is 0.3 or 0.03 micron only, 0.3 micron. So now we are talking, we are coating with 3000 Armstrong and 300 Armstrong. It's a maximum number, 1500 to 3000 Armstrong unit. Armstrong only we are quoting, not yet. This thickness of this material is 600 to 700 micron, roughly less than 1 mm, let us say. This particular flexure is 20 micron. On that, we are having some Armstrong unit coating. This coating is done at elevated temperature when you are doing what is called evaporation techniques. Now you see that this thing, when you are coating, what is happening? During coating, this material is subjected to high temperature and the temperature expansion coefficient of these pots is very, very less. That is why these materials are selected because of one of the characteristics, this is 0.5 ppm per degree centigrade. That means it is very stable with respect to temperature also. But when you are this material, when you are coating, we are taking it to 250 degree. It is not expanding further. But during coating, after coating, you just see that chromium and gold expansion or the coefficient is temperature coefficient of thing is 14 ppm and 7 ppm. That means when you are coming down to 25 degrees centigrade to the room temperature, after coating, this material, what is called subjected to thermal stress. Now, bottom you are seeing, no? In a left side, if you are seeing this horizontal, it is there. A pendulum is horizontal. When you are coating, it is like this. When in the after coating, when it is coating, and after that we are coming back, it is having a bimetallic effect or whatever it is. So now what happens after the coating? Now you see that there is a deflection or a permanent stress on that. This stress over time, it is increasing or decreasing, it is yielding. It is a creep phenomena is formed. This is what the phenomena we found out. We found out like this literature, it is there, patents are there. That is why I don't know 1400 degree. QA 1400 to QA 2000 to QA 3000. When you are going through the process improvements through patents or any other place, if you are going through, you will be understanding that they are improving with the process techniques, which is creating, which is the cause for the many problems. This is what I meant, because we have to correct the process in 3000 Armstrong unit, which is that layer also. This is the area we are discussing. That is what. And one more thing is wherever the pendulum is sitting on the material, that material also should have expansion coefficient less. That is why people are selecting what is called the matched materials. I told you material is matched. That is fused quartz we are taking. Whatever is sitting, touching the fused quartz with the magnet housings, what is called outer housings, all the things. These materials have to be selected. So material selection onwards, process onwards, design onwards. If we are working together in tandem, then only these type of sensors possible. Okay, next slide. So now MEMS sensor, now if you are taking equivalently MEMS sensors also, we are seeing that in that flexure, mainly the MEMS sensors, they are using silicon as a base material, silicon dioxide, which is coated on the silicon surface micro machining also, they are doing that. That if you see numbers are small, but this process induced stresses is not totally eliminated in these what is called silicon MEMS. That is why we are not able to achieve the highest accuracy. Otherwise, it is a large number producible, but we are not able to achieve the highest accuracy. Next thing go. And these are all the different what is called now flexure. On that day we are seeing the top right, you are seeing a flexure, a flat leaf flexure you are seeing, but there are so many flexure configuration for the MEMS because the n number of designs are there. We are not going into that. Next. So this is now if you see typical MEMS specification, if you see this range is very less and the sensitivity in volt per millivolt per thing there is no stability numbers will be given. It is in milligauss only, it will be there. Okay, next. But power dissipation is less, price is less. Now we will come back to the, we are having only small doses. Okay, this is gyroscope to measure the what is called. Next you go. So we will not cover so many things. Okay, go. So now there are progress in the what is called the history is actually mechanical gyro to ring laser gyros and ring laser gyro and fiber optic gyros are optical gyros. Previous slide, that alone you just previous slide go. Previous slide. Also now if you see second one is an optical gyroscope, in that fiber optics gyro, ring laser gyro is there. That is what next. In that if you see then the previous slide. If you are taking RLGs, ring laser gyros are discovering 10⁻³ degree per hour accuracy, and the range is also very high range, 1000 degree per second it can go. But now slowly FOG is emerging, but its FOG resolution is very less for some reasons. Okay, next you go. So now if you see that whatever this is again performance of the gyroscope in degree per second, what is the requirement for different applications and its stability requirement, next column. biostability column, that different applications, what are all things required. We will not go to that. Next thing. So this is straight away optical gyroscope follows the Sagnac effect. Next. Hello. So typical interferometer, if you are taking some Michelson interferometer, you are aware that it is the what is called path length difference between the two beams. It is measured as the what is called the interference between two different beams. That is used for the what is called measuring things. Now next you go. This is using laser. How we are doing next. This is in Sagnac interferometer. What is coming is it's a closed interferometer. It is not an open interferometer. So simultaneously, two beams are formed in a clockwise direction one and counterclockwise one. Two beams are formed. When it is stationary, when it will come back, the path difference will be same. So it will be having a bright fringe at the detector point. When it is rotated, this blue and when it starts, it will be starting at one particular point. When it is rotated, it will come back and there will be a fixed path difference. So this path difference due to the rotation between two counterclockwise beam is the measure of the what is called the rate. This is what found out by Sagnac. Now next slide you go. So now you see that now that is path difference. If you want to find out, that is velocity of the light, time, C into T is the difference. Path length difference is Ct plus minus Ct minus delta L. This is a path difference. Path difference converted into phase difference. Phase difference is the measure of the other one. Next you go. So now if you see some numbers alone, we'll just see if you are talking about, when you are talking about degree per hour, this earth rate is 15 degree per hour. To measure the earth rate, this because now this ring laser gyroscope, it is Sagnac in active interferometer. What is happening? That is the number of what is called it's a mode. We will tell that m lambda. This path length is converted into a frequency difference through this one. This frequency active ring laser. This is what the frequency is varied. This frequency and this frequency. There is a frequency difference when it is rotated. The frequency difference is converted. Frequency difference is the measure of what is called the rate. So frequency difference, what we are supposed to get is 7 Hz per 15 degree per hour. When we talk about 0.01 degree per hour, if you want to have, we have to divide by 1000. So that means roughly we have to get what is called the 0.07 or not 7 Hz we have to measure. 7 millihertz we have to measure for 0.01 degree per hour. This is what the way we are working. So that means this, even though we are talking principle is very simple, but when a measurement area is very, very small. Okay, next thing. So this is again, it is told that what is the phase difference is something around 10 power 8 radian and delta path difference is 10 power minus 15 meter. It's a femtometer we have to measure it. Optical path length of the order of 10 power minus 15. That means whole different system should be very, very stable. So small path difference only is giving that much accuracy. Next. So this advantage of ring laser gyro is a high level of accuracy, wide dynamic range. That is the very large rate and very small resolution. And it is instantly, it is operatable. It is because it's an optical gyro, it is not sensitive to acceleration and temperature, no moving parts. So for that purpose only, this ring laser gyro is very much attractive. But the technology is so complex, it is not available, the technology is not available to others, and making that sensors is very, very difficult. Next thing. So there are 2-3 configuration mirror-based laser gyro. That means now there is a triangular block. There are 3 mirrors. This you can see the 3 mirrors are there. This clockwise and counterclockwise beams are rotating in that, means moving in this thing clockwise and anti-clockwise. There is some portion is coupled outside for measuring the interference fringes. When you are giving a rotation, there is a fringe continuously it will rotate, move. That is because of the frequency. That is a measure. Now, right hand side you are seeing instead of mirrors, prisms are used for that purpose. Okay, next. So requirement for laser gyro is a highest quality resonator. It is required. That means people are using this particular resonator block is a what is called ceramic material that is zero expansion coefficient material we are using. Light laser, it is there. Laser is inside itself there. Single mode laser, single mode operation. It should be single mode. It has to work stress-free assembly. Okay, all these things are requirement. Next thing. So now mirror-based are the block and all just shown that, okay, next you go, because the time is not the next you go. So now the important point is making everything is easy, principle is easy. But this light, even though we are telling that it is insensitive to many things, it has to pass through the prism or it has to reflect by the mirror. Mirror is having a coating. On that mirror, it has to reflect. That means there is an interaction between light and medium that is sensitive to temperature, stress, magnetic field, electric field, intensity, acoustics. This is a problem because now this is environment or any change in environment, anything happens, it is affecting the media through so many what is called the principles, that is thermo-optic effect, stress-optic effect, magneto-optic effect, like Kerr effect, like that many things are there. So this even though light is, we are telling light, but light is sensitive. When it is going through some medium, it is sensitive to all this external field. So this has to be controlled. There only the problem comes. Okay, next week. So this, okay, now with that, I'm closing that other one, RLG, very small thing only I put it. Fiber optics gyro, it is now there on RLG, light is passing through the air or the vacuum it is passing through. But here the light is passing through the what is called fiber. It's a material inside the fiber. Same interferometric principle only used. This is technologically it is better than the producible, better than the ringless gyro. But this also is subjected to, because very long fiber length is required for getting the phase difference. Now the phase difference, now right hand side one formula is there, that is depending upon the area or length, total length of the fiber. If length is very large, you will get a larger phase shift for this one. So that is why bottom it is written. Next thing. So now this because we talked two moving elements, both are at very high speed, that something 11 km per second it is moving. So there will be a relative movement between that. The relative motion is to be controlled. This is what the major challenge. Now next thing go. So now there is a target, there is a chaser. Both are separated, then it has to be aligned, it has to dock each other. This is what our requirement per se. Now here major problem is if you are having a navigation sensor alone, now you have seen that with respect to time, it will drift. That's what they used to tell, that it has drifted. We are not able to dock it now. That's if we want some more characterization. All the things are told like that only. Because with respect to time, accuracy even though better, micro-Gs are the degree per hour. This with respect to time, it will, what is called error will be growing. That error need to be controlled. So this inertial sensor, with the inertial sensor alone, we will not be able to dock. So we have to go for multi-sensors. Next thing. So now you see that both are, when the velocity difference between the two things are 2 mm/second difference. This is 11 km per second, but the difference between these two are 2 mm per second. At a distance of 1 kilometer, it will take 138 hours. But when it is coming closer, within 1 meter when it comes, 2 mm/second means within 8 minutes it will hit and collapse. So this velocity has to be, relative velocity has to be killed. It has to be brought down to zero. Next slide you go. So now how the people are doing, it is not sufficient that only inertial navigation sensors are not sufficient. We have to go for multiple sensors, vision-based navigation sensors, or the proximity sensors we have to have. So proximity operation, all these proximity sensors are there. Because it has to be oriented relative to the another spacecraft, some pattern matching is also there. So these are all the chaser and target. Next thing go. So now if you are taking the bottom graph alone, you just see that one sensor alone will not do. So multiple type of each range, we have to have different sets of sensors. It is required whose sensitivity is very good and accuracy is also very good. That means when you are going closer and closer, the sensitivity should be very high and the accuracy also should be very high. That is what the thing. So next thing. So now that is why camera-based pattern tracker, laser range finder, optic flow meters, then proximity sensors are used between these two things. Now what I wanted to tell here is navigation system alone cannot work. Next slide. Go. Pure navigation sensors, whatever we are talking, the accelerometer gyro-based INS alone will not be sufficient to dock it. It needs many things, many proximity sensors and other range finding sensors and cameras for orientation finding, pattern mapping, everything is required to think. Here also that same planetary landers also similar concept only, because we have to land at a place where there is no what is called debris or the what is called the other hazards should be there. So we have to do like that. For that, relatively we have to position it at zero speed. Okay, now next you go. So for that, now these are all known. Now next you go. So now in the lander, next you go. So in that lander only, we are Chandrayaan. If you are seeing that all these sensors, this is the LIRAP is the IMU that is used for velocity and angle only for the orientation change. How much rate we have to give like that to control purpose. But we having an altimeter, lander position detection camera, hazard detection camera, laser altimeter, laser Doppler velocimeter. Like that, many numbers of sensors are used for the landing purposes. Next. So now what it does, each sensor does what it is mentioned here left side. Now you go to the next one. So now you just see for autonomous navigation purposes in the relative motion, relative navigation when you are going for in an autonomous mode, we need to have many number of sensors. That is why the multi-sensor navigation is required. Now gyros and accelerometer, inertial sensor there, other sensor is there. So many proximity sensors. Left side you are able to see. A reference sensor also that we have to refer it with respect to sun and star, the orientation between satellites and the orientation of each satellites. Everything is required for that localization, mapping, path planning and control. So that multi-sensor navigation is required. The next you go. So now this is now one next immediately to come. This is autonomous functioning. We are having autonomous cars also using the same type of things. Then why it is so critical there? I mean, that's what I told. No, that is the at what rate we have to do that. What rate and what accuracy requirement is there? And the minimum what is called the processing time we have to do. Here in this thing, even though we are having similar items, these accuracies are different. You are having a lot of time to act in that, not in milliseconds, in seconds only. So those way only it is different in the car. Now next you go. So now the similar function is done by tiny ant also. If you are taking ant also is not doing only one element. It is doing n number of elements simultaneously. Optical things you are using. That next to feeder it is coming back. When it is going to searching on food, it is going zigzag way right hand side. When it is coming back to the nest, it is going straight line. So this type of what is called navigation, how they are mapping it, how it is performing. For that, no, what are all things they are using it? No, you just come. If a navigation aid used in previous slide, that is step counting, odometer they are using, compound eyes they are using. Compound is black and that is this ant eye is very small. No, that is with that eye itself it is performing many things. Now next you go. If you take the tiny ant, it is doing visual. They are using eye with that eye and ocelli. Ocelli is a three thing in the in the eye means. Just a center point it will be there. So if the ocelli, they are means polarization, compassing, imaging, brightness monitoring they are doing with that. What is called path integration, landmark guidance, visual piloting, head stabilization, route through what is called the chemicals. All these things are done by an ant. So tiny ant also. So what I want to tell is, it is not that we are only doing that, but we need to do in a different fashion. That is what the only difference. Next thing. So now system now you just see okay how we are doing that. It's a conservative design only. It is now a lot of margin we have to keep it because over time it has to perform. So extensive testing has to be done. Operation plan is also next. I'm not dwelling on that. Next you come. Here only one part because now you test as you fly. That is the success for the any mission. So we have to test what is happening in the landing. The similar operations it is tested in ground. In ground, complete mission planning is done and it tested here. So test as you fly is very, very important for space missions. Next. So now this is what now, because now margins we are keeping large, that is operation environment may be small, but acceptance environment will be, the limit will be more. Qualification environment will much more. Design robustness will give so much more. So we have to qualify the sensors and systems to the maximum limit and maximum duration so that the endurance is built into the system. So now next you go. So now for that only is very important thing is for space system, the one concept is the system engineering concept, because many number of domain experts will be there in across the table, science, engineering, application, technology, everything will be there. They have to discuss together. A collective wisdom is used for resolving things, because every component change in every area can affect the other areas. That is why a system engineering concept is required for this type of space systems. For other systems, it is not so. Next thing. So again, I come back to the same slide telling that autonomous function, it is required. Faster rate we have to get an accuracy. It's very costly affair. It's a risky thing. So space systems are very critical for that. Maintaining quality aspects to the highest level is required. One or two examples only I told that because of limited time. Next. So now again, all this part, performance, features, reliability, conformance, durability, serviceability, this is applicable to space systems also, not only for ground systems on the common products. It is required, but in a different perspective, different accuracy levels. That's all. Next. Thank you. This much only. I could not explain much longer for the English and gyro due to the time limitation. Sorry for that. But otherwise, I'm closing this meeting. Now, please, if you are having any questions, please ask me.
Dear participants, do you have any queries?
If it is not here, then any other thing is required in things. We will send some slides also if it is required. Please put it to the convener. Questions or any requirement of any further explanation on that. I will put it in slides form and I will send it to the convener of this meeting.
Thank you, sir, for the insights you have provided on the criticalities in the quality aspects of inertial navigation systems. We have understood the challenges in space environment like vacuum, radiation, and microgravity. We have got an introduction to the guidance, navigation, and control functions in a launch vehicle. We have been given an overview of the attitude, determination, and control system functions. We have got an orientation towards the inertial sensor technologies. Different types of gyroscopes and their applications are explained in a concise manner. Relative navigation for docking and precision soft landing is well explained. The depth of knowledge shared has truly expanded our understanding of how precision and reliability drive success in space technology. On behalf of Marthandam College of Engineering and Technology and participants, I extend my heartfelt gratitude to our esteemed speaker, Shri S. Pal Pandian, for delivering such an engaging and enriching session. Your expertise and insights has shed light on the critical role of inertial systems and the unwavering commitment to quality that ensures mission success in space exploration. Your session has truly inspired us and broadened our perspective. Thank you, sir.
Thank you very much. Thank you. Thank you very much. If at all any further things are required, please let me know. I will just share the information what is available to enrich you. Thank you very much.
Okay, thank you, sir. Now, as we move forward, it's time to begin session 4. I'm delighted to invite Dr. Bleslin Elizabeth, Assistant Professor, Department of EC, to take charge of the session. Over to you, Dr. Bleslin Elizabeth.
Now, we move on to session 4, which focuses on fundamentals of space technology. We are honored to have Sri Shaji Simon, Division Head, ISRO Inertial Systems Unit, Vikram Sarabhai Space Center, Trivandrum, as our speaker for this session. He has completed his BTech in College of Engineering, Trivandrum. He is an expert in research, development, and realization of solar panel rotating mechanisms and power transfer systems in various satellites developed in ISRO, including Chandrayaan Mars orbiter missions. He is a team member in launch activities of GSAT-16 satellite in European Space Agency at French Guiana, South America. At present, he is a division head in ISRO Inertial Systems Unit VSSC and authority to certify the quality and reliability assessments of various electromechanical systems developing for satellites and rockets. With such an impressive background, we are privileged to have him with us today. Let us extend our warm welcome to Sri Shaji Simon as he shares his expertise with us. Thank you, sir, for joining us today. We are eager to hear your insights on fundamentals of space technology. Sir, please take over the session. Over to you, sir.
Yeah. Good evening. Are you hearing me? Hello, are you
Yes,
hearing
sir.
me?
Yes, yes.
Yes, sir. Yes.
Yes, sir.
Good evening. I am just giving you an overlook of our fundamentals of our space technology. So this may be a little simple, not as much complicated as what earlier sessions. So I have to stop at 9 o'clock, isn't it?
Yes, sir.
Oh, okay. So let me start with that first slide. So you may be aware that our inspiration was our earlier President Dr. APJ Abdul Kalam. He was there in VSSC for many years, and the bottom figure you can see Dr. Kalam is assembling the AA rocket. So that figure shows his earlier days in VSSC. I'll just start with the basics of rocketry. See, you can see this is our solar system. So in the solar system, you can see the Earth. This is the here only human or creatures are living. So why it is living? Because our Earth is the third planet, and we are having an atmosphere. You see, Earth is not far from Sun. It is the third planet. So if it is the position of the Venus, the temperature will be very high, so that humans or creatures can't live. If it is a place of Mars, the temperature will be very less. There also humans or creatures cannot live. So Earth is the only place where we can live without any external aid. That is, any blanket is not required, or any the type of suit is that is the space suit or anything is not required. We can freely live. And here is the only planet where water is available naturally in three forms. So ice, water, and steam. So that is why our Earth is very much feasible to our life. And going to the space now, first of all, first we will define where is space. So on the left side, you can see there is a that is 0 to 20 kilometer range that aeroplanes are there, 50 kilometer range weather balloons are there, but 100 kilometer, it is called a Kármán line. Because it is based on a scientist, name of the scientist called Kármán. So how we define space is that above 100 kilometer, we are segregating from our space. So if somebody goes 85 kilometer and come back, then we are not telling that he has gone to space. If he crosses the 100 kilometer line only, this Kármán line only, then we will define as he has gone to space and came back here. So the conditions of space, there are lot of debris are there, then extreme the temperatures are there, then charged particles, and the zero gravity, then a lot of magnetic field, deep vacuum, and radiation. So among all these radiation or this magnetic field, our atmosphere is protecting us. So that is the condition of our space. And you can and you see a lot of satellites are revolving around our Earth. So how these satellites are staying. So if we throw a stone from the top of this thing, it will reach somewhere here. And if we give more speed or velocity, it will fall here. But when it reaches the escape velocity of 11.18 kilometer per second, it will go around the Earth. So that is the basic principle of our satellites. So there are two forces. One is Earth centripetal force and the centrifugal force due to the rotation of the velocity of the satellite. So what our rockets are doing, we are giving velocity to the satellite with the help of the rocket. So that velocity is required for orbiting satellites around the sun. So this is the basic principle of the satellites rotating around the sun. This is called continuous falling. And you can see the rocket and aeroplane. What is the difference between rocket and aeroplane? See, aeroplane means it is air and plane. Without air, aeroplane cannot work. So when the velocity, and that aeroplane needs a runway. So in the runway, when aeroplanes gets velocity, the air will hit on the wings of this aeroplane, and it gives an upward thrust, and thus it is flying over, and it is flying over the air. So rocket means it does not need any runway, it's directly going up. And another difference is that aeroplane, we are putting fuel only. For burning the fuel, oxidizer is required. So that oxygen, it is taken from the air directly, as like our vehicles, no, car or buses and all, no, if you are putting diesel or petrol only. So the oxygen for burning is taken from the atmosphere. But in rocket, it is going to space. There is no air available or oxygen available. So in the rocket, we are taking fuel as well as oxidizer along with them. So that is the main difference between the rocket and aeroplane. And the fundamental basic of this rocket flight is Newton's third law. Every action, there is an equal and opposite reaction. You are filling fuel in the rocket, and inside that fuel burns, and it produces energy, and it passes through a nozzle. It creates an action, or that exhaust creates an action, and that opposite side, as per reaction, the rocket moves. So this is based on the third law. So that evolution of the rocketry, it starts to China, because that gunpowder was first invented in China. You know, any scientific inventions, if from the history of the our world, if we are getting any inventions, first we are putting it for attacking. So these gunpowder, first they are using that fire arrows. So to enhance the uh, uh, distance of these arrows, they are using it as in fire arrows. Then you can see that Van Hu's flying chair. This is Van Hu was a Chinese emperor. Like every people, he also want to fly over the sky, like birds are flying and all. No? So from ancient time onwards, we are having intention as like flying like a bird. So after the invention of this gunpowder, he put some 32 or 40 numbers of rockets around his chair, and he told his servants that you have to be ignited all in a same time. And that emperor, no, so he thought he will go to some other places and he will see other people. So he want to show that he is an emperor. So he put all his costumes as like an emperor, and he died. But what happened after some time, all thing fell down, and he has died. So we can think that what a foolish idea it is, but that day people's intuition to fly and all these things, no, that do experiments, that we have to appreciate. These are the earlier rocket technology scientists. I think you may be aware of all these people. So our space era begins. First, 1957 October 4, the first man-made Earth satellite, it is launched by USSR and opened the way of space exploration. You just know it is only 83.6 kilometer weight and just half meter diameter. That was the first man-made satellite, Earth satellite. And you can see the first lively body gone to space is Leica. That's a dog. This in November 3, 1957. And the first man gone to there is Yuri Gagarin. And the first woman has gone to space is Valentina Tereshkova. All other are India in space. See, when our space program started in 1962, so based on that, 1962, we are started the space program, and our space program was very modest. And first we started the space program in Trivandrum, Tumba. It is called Tumba. So there is one church. It is Mary Magdalena Church. There only in 1962 this first laboratory has started. Still, that church is available in our office, and it is keep as a space station. And you know that Sarabhai is basically hailing from Gujarat. Why he has come to Tumba or Trivandrum for this for the starting of the space program? See, you know, Earth has magnetic poles, North Pole and South Pole. So there is a magnetic equator which is passing through the Tumba. So in this magnetic equator, the magnetic forces are becoming null. So we will get more information about the atmosphere or the space or thing if we are sending meteorological rockets uh, at this magnetic equatorial area. That is why Tumba is selected as the first rocket launching station. It is TERLS, it is called Tumba Equatorial Rocket Launching Station. That's why Tumba has selected as Indian Space Program headquarters. See, these are the first rockets sending from Tumba. In 21st November 1963, the first sounding rocket is launched from Tumba. That is basically Russian rockets. And you can see the system of rockets assembling, transportation down and all this during these 1962 times. These are the first beginning of our rockets. You can see this is APJ Abdul Kalam and this is Dr. Sarabhai, who were the first pioneering of our program. I'll show you one video. I think it is not working. So, as I explained, this is the first, this is the basic rocket principle. So, it is having an oxidant and a fuel, and these oxidant and fuel has burning in the combustion chamber. It produces energy, and that passes through the nozzle. It creates thrust, and the rocket moving upwards. So this basically this concept has developed by Silkovsky. He is an ordinary high school teacher in China, and it was become practically built by this Goddard. These are the basic rocket propulsion systems. The first one is there are three types of rocket propulsion fuels. First one is the solid. Solid one is the ammonium perchlorate is called. So it is what is it? Cast. It is as a slurry form and it is cast inside the solid motor, and the center it is igniting. Then it will fire and produces energy, and it is passing through the nozzle and it creates thrust. The another one is this is the liquid rocket. So here the fuel and oxidizer, they are mixing together and with a turbine, it is going to this combustion chamber, and through nozzle, it is firing. And the most advanced one is the cryogenic stage. Here, the hydrogen is the fuel, liquid hydrogen is the fuel, and liquid oxygen is the oxidizer. This is a very complicated mechanism because the freezing point of water is 0 degrees centigrade, and liquid hydrogen exists only at minus 253 degrees centigrade, and liquid oxygen exists at minus 183 degrees centigrade. So maintaining this temperature is a highly complicated technology. That's why this cryo engine is always a highly complicated technology. This is the basic thing, fuel plus oxidizer. This is another schematics where the fuel plus oxidizer burns and it produces thrust. These are the launch vehicles of India. First, we started with SLV-3, where the project director was APJ Abdul Kalam. Then ASLV, PSLV, GSLV, and GSLV Mark III. See, these are the approximate sizes. Approximately, this is some 12-storied building height. It is there. If you are directly seeing it, you can see the exact size. This is the exploded view of a GSLV rocket. Here, 2 points are there. One, this is the satellite. The satellite is called the payload. Payload means it is giving us money. Payment it is giving us. So the aim of the rocket is to just inject the satellite in the prescribed orbit. That is the aim of rocket. So rocket is only a vehicle to inject the satellite. So satellite is the payload. So while you are considering about the parts, here there are 2 payload fairings are there. Payload fairings, it is called that heat shield also. The name heat shield also it is called. Why it is required? Because we are our Earth having an atmosphere. So while the rocket moving through the atmosphere, high heat is generated. So that heat will affect the functions of the electronic systems inside the satellite. So in order to protect the satellite from the high heat, we are using the payloads or heat shields. And after we are completing the journey through the atmosphere, the payload become separated. And here the rocket is made up of many stages. Why this is the first stage, second stage, third stage? Why the rocket is made up of many stages? That is, see, when the rocket fires, it produces a thrust. So basically, thrust means mass into velocity. So whenever the mass reduces, the velocity will increase. So when the rocket is at the launch pad, it produces a thrust just to lift the rocket. So then after lift off, it gradually getting velocity. So how it is happening? The mass reduces, then the velocity increases. So how this mass reduces? While the fuel is burning, the mass of the fuel is reducing. So gradually the mass reduces, and accordingly the velocity has increasing. And that first stage, when it is completed this firing, that stage cases having very high mass. So what we will do that first stage, that 4 strap-on rockets and the center stage we are separating. While separating, lot of mass is getting reduced, and correspondingly that velocity has increased. That is why we are making the rockets as various stages. And you can see there's strap-ons, that additional rockets we are mounting at the bottom of the rocket. Why it is required? Because from the earth, if you are starting a rocket, maximum energy required because of the gravitational force of the earth, gravitational pull of the earth, maximum energy is required when it is lift off. That's why additional rockets we are mounting at the bottom. So that velocity addition, these stage separation, we are getting the velocity additions because of the high reduction in mass, and finally it will put the satellite in the specific orbit. Here you can see the assembly at Sriharikota. This is all stages are brought from VSSE and Bangalore and various other centers, and it is integrating here. So you can see the vertical integration unit. Here you can see lot of platforms are there. They are bent to the mainframe. So when each stages are assembling, these platforms they are put it as a horizontal platform, and people stand there and assembling. So after each stage assembling, these platforms they are folded to the side panels. So finally here you can see all the platforms they are folded to the mainframe, and the total rocket is taken out from the vertical assembly building. Here left side you can see the satellite is assembled at the top, and that heat shield you can see, or payload fairing you can see. And the final assembly of the satellite, then all the platforms we are folded back, and then it is taken out of the vertical assembly building, and then it is going to the launch pad, and we are at the launch pad, we are launching the rocket. So this is the launch control center. These all are at Sriharikota. The rocket is taken out from the launch pad, vertical assembly building to the launch pad through rails. So, and these in this launch pad, there are umbilical cords are there. So that is the final connection when it is in the launch pad, and during the launch time, these umbilical connections are get cut, and it will go. This is a assembly procedure. This is a strap-ons first stage. So first stage is assembling on the platform. And this is the strap-ons. So the assembly started from the bottom. So that strap-ons they are assembling with a crane. So 4 strap-ons they are assembling at the bottom. And now this is the liquid stage. So it is brought from Valiamala LPSC. Then it is using a crane, it is placing at the top. So there this temporary platform people are sitting. And This is the cryogenic stage. So it is brought there at Sriharikota. And it is assembling. Since it is contains liquid hydrogen and oxygen, so a thermal protection layers we are applying at the outside. That is why it is seeing as a black color. And this is the cryogenic engine. So this is a very complicated engine because it has to handle the liquid hydrogen and liquid oxygen. And after all testing, it is assembled to the rocket. Very critical assembly, this cryogenic engine. And this is the satellite. It is assembled in Bangalore, and after this full assembly, it is brought to the Sriharikota. These all are the antennas has deployed. Thermally insulating sheets are, that is golden color sheets, multi-layer insulation they are applying. This is the solar panel, and it is folded and it is assembling inside the heat shield. So after the full assembly, it is taken out from the vertical building through railings. Yeah, it is taken out and it is going to the launch pad, and where it is fixing at launch pad. And from launch pad, it is launching. This is the fundamental assembly sequences of a typical rocket.
L40 is having.
This is the rocket launching. I think yesterday also you have seen. You can see our spaceport, that is Sriharikota Satish Dhawan Space Center. Now it is called SHAR, Sriharikota. See, initially I told our space program started at Trivandrum, and we are having meteorological rockets sending from Tumba. But the satellite carrying rockets we are sending from Sriharikota, not from Trivandrum. Why it is happened? Because our space program started at Trivandrum, and the satellite rockets are sending from Sriharikota. See, the right side you can see this is our Earth rotational speeds. See, at the equator, the Earth is rotating around 1,650 kilometers. That is Earth rotational velocity. So the Earth rotates from west to east. So when we are launching rockets towards east, what is the advantage means that velocity 1,650 kilometer rotational velocity we are getting. That means that additional velocity we are getting for launching. As like if we are doing a long jump, they are running and doing jump. So that more distance they will cover rather than standing and jumping. Like that, near the equator, if you are sending a rocket to east side, we will get the advantage of this 1650 kilometer per hour speed also. So if we launch a rocket from Trivandrum to east side, it is very problematic because the stages will separate and it falls on populated areas. But if we send rockets from east side and that east side, if it is sea, that means that stages, the separated stages all fall in the sea only. That's why we are selected the Sriharikota, because it is on the east side of India. You can see various rocket launching stations. So this is the equator. So where's best rocket launching station is French Guiana. It is almost below the equator. That French Guiana, see, the European nations, they are using the rocket launching from French Guiana because they are having a colony here. So that there they are developing the launching station. USA that NASA launching station Florida is somewhere here. It is not exactly under the equator. So here we are having, okay. So now I am telling about the orbits and that coverage geometry. See, you can see that 3 satellites at 180 degrees centigrade at 36,000 kilometers. So these 36,000 kilometers, it is called a geostationary orbit. Why it is called a geostationary orbit means at 36,000 kilometers, due to this Kepler's theorem, each orbit having a horizontal velocity, that orbital velocity. So at 36,000 kilometers, that orbital velocity, if the satellite rotates, it is the same as Earth orbital velocity. So what happened at 36,000 kilometers, if one satellite rotates, if we look it from the Earth, we can see at one point it is directly looking to that point. So that is why it is called the 36,000 kilometers is a geostationary orbit. So in any country, they are sending satellites, that is communication satellites, that is horizontal to the equator plane. All countries put communication satellite at 36,000 kilometers. So there are if 3 satellites we are putting, see, if 3 satellites we are putting, we will have global communication. That is, if we want to see, if we want to what is it, call to America, so we are having 3 modes. Either we have to put a cable from here to America, or we have to do microwave stations in between. But we cannot span these microwave stations much more because Earth is round. So that communication will be disturbed. So putting cable from here to America, it is very difficult. But if you are placing 3 satellites at 36,000 kilometers above the Earth, we can do the global communication very easily. So this concept was uh, uh, first told by Arthur C. Clarke. But that when he was explaining this concept, there was no satellite. But he's having a dream that if we are putting these 3 satellites like this, we can do the global communication. These are the basic parts of our satellites. So it is having 2 reflectors. From the ground, we are receiving signals, and we are sending it, uploading and downloading these signals. And at 30,000 kilometer, we are putting it as a reflector and receiver. So these are the basic parts of the satellite, where that the fuel tanks are there, solar panels are there, batteries are there, then reaction wheel, momentum wheels are there, thrusters are there. All these things are joined together. It's become a satellite. This is one satellite we are assembling in Bangalore. See, now what are the uses of satellites? I think nowadays we cannot live without satellites. See, if we are if we are putting our ATM card, which is having an account in Trivandrum, if we are putting in Simla or Delhi, within fraction of second, we will get money. That is because of through these satellite communication. And in our mobile phones, if you are searching something, if suppose your college name, if you are putting the in a very fraction of second, you will get the result. How it is happening? Because your college name and all these things, that is that site is placed in California, and from our mobile it is going to one satellite, and from there it is going to other satellite, and it is going to the Google office in California, and from there a particular building, particular floor, particular room, particular almara, we are putting this data and collecting it and bring back to your phone. So these all are happening with the help of the satellite. So without satellites, we cannot live. This is one imagery of Rameswaram temple. This is Cartosat. This is the way in which we are sending Chandrayaan. So these are the orbits we are made, and based on this orbit correction, we are reaching the Chandrayaan. So these are the basic the principle of our satellite orbits, that Kepler's law of planetary motion. So here you can see when this higher side is called apogee and lower side is called perigee. So based on the Kepler's law, at higher side that satellite will rotate slowly, and when it is coming to the apogee, it will rotate faster. So this is the interplanetary operations. We are using this method. This is the Earthrise seen from the moon. So we are having this Mars orbiter mission program. So you can see that departure from there, it is December 1st, 2013. And that time our Mars is here only. So when it moves, and when it reaches this place where September 24, 2014, that time that Mars also coming. So both are joined together, and then only it captures this moon. So how much precision we are required for getting for sending a satellite to Mars. So this is the sounding rockets from Tumba. You can see that, and this is a space museum at VSSC Trivandrum. So if anybody wants to visit VSSC Space Museum, you can come through the site. You can apply and come. These are the, you can see the space debris, lot of satellites from earlier onwards it is sending, and now it is much more populated. You can see this is the International Space Station. This is almost the size of a football court, and it is around 450 kilometer height. It is rotating, and still people are there. And you may be aware that Sunita Williams is now here, and just it is available in YouTube. Just I am showing this, that zero gravity.
Hello, I'm Sunny Williams. I'm up here on the International Space Station. So this is Node 2. This is a really cool module. Of course, most of these modules you'll see, they have 4 sides, and they're put together. That way we could sort of work on a flat plane, either a wall, a floor, another wall, or the ceiling. But, you know, again, all you have to do is turn yourself and your reference changes. The reason I'm bringing that up is because this is where 4 out of 6 of us sleep. And so people always ask about sleeping in space. Do you lie down? Are you in a bed? Not really, because it doesn't matter. You don't really have the sensation of lying down. You just sit in your sleeping bag. So here's one sleep station right here. I'm going in right now. You can follow me if you want. So I'm inside. It's sort of like a little phone booth, but it's pretty comfy. I've got a sleeping bag right here that we sleep in, so we don't have sort of like a little bit of a cover. We don't fly all over the place. But you know, you can sleep in any orientation. I have it feeling like I'm standing up right now, but like you saw, I'm on the floor. But it doesn't matter if I turn over and I sleep upside down. I don't have any sensation in my head that tells me that I'm upside down, so it really doesn't matter. The sleep station is also like a little office. We've got a computer in here. As you can see, we've got a couple little toys. I've got some books. I've got some clothes and other things that make it sort of like home. I'm coming out. And just for reference, that's one sleep station. This one's another, right here. There's one on the ceiling, if you want to call it, right here. And then there's a 4th on the other wall over here. So all of us sleep in a little bit of a circle. All right, come on back. There's more to show you. I know that there's some questions about how do you use the bathroom, and how do you actually live in space like normal, like at home. I mentioned real quickly about getting up in the morning and brushing your teeth and washing your face. Well, how do you do that? Well, here is the bathroom, essentially. You get up in the morning, and we have a little kit, and it has all the essential things that you need, like your toothbrush and toothpaste and brush. See how much better the brush makes my hair look? I'm just joking. It still stands up straight. It doesn't matter where you are. It's always going to stand up straight while you're up in space. A lot of people ask about toothbrush and toothpaste. So luckily enough, toothpaste, you can do it upside right this way, is sticky, and so it sticks to your toothbrush, no problem. Another cool thing is that water sticks to your toothbrush too. See it? I'll have some water come out. Water is pretty neat up in space. It'll stick to your toothbrush. It will make a big bubble. That's just by surface tension. And then you can drink it. So a lot of people ask about what do you do with the toothpaste after you brush your teeth. Two options. Swallow it, and it's sort of like mouthwash, but it tastes a little gross. Or you can just spit it out in a paper towel, and then you don't have to worry about it. Swallowing thing I wouldn't recommend at home. I'm only up here for 4 months, so it's not that bad. One of the most pressing questions about living in space, of course, is the bathroom. So let's take a look at that little piece of work. Come on in. Here we are at the throne. This is awesome. You might see the little, you might have noticed the little moon on the outside. This is our orbital outhouse right here. And of course, it serves for two functions. Number two, right here. I'll show you. You see it's pretty small, so you have to have pretty good aim, and you be ready to make sure things get let go the right direction. And it smells a little bit, so I'm closing it up. And that's, of course, for number two. And this guy right here is for number one. So they're sort of two slightly separate functions, but you can do a little, essentially both, by hanging on right here and doing number one and number two. I might add it's color coded, so you really don't get it mixed up, which is nice. This is yellows for number one. And also, there's a selection of paper. People always ask about toilet paper. What do you do with toilet paper? What kind of toilet paper do you have? We have gloves, just because sometimes it does get messy. We have some Russian wipes, which are a little bit coarse if you like the coarse type of toilet paper. We have some nice tissues, which are nice and soft if you like soft toilet paper. We have Huggies, just for any cleanup. You know, we were all babies once, and this sort of helps. And then if things get really out of control, we have disinfectant wipes, just to make sure we clean up here. Because, you know, just like the water I showed you, the number one stuff can sort of go all over the place if you don't aim correctly. And did I mention both of these have a little bit of suction, so they should keep things going in the right direction. But like I said, sometimes things get a little out of control if you are out of control yourself flying around. So we have lots of protective stuff. And of course, you do have your privacy. There's a little door. So other people know that you're in there. Here's a pretty cool place. This is sort of like in your house where everybody meets in the morning. After you wash your face, brush your teeth, you want to find something for breakfast. And this is our kitchen. You might notice there's all sorts of foods here. It's like opening the refrigerator. You got all your different stuff that you want to have: drinks, meats, eggs, vegetables, cereals, bread, snacks. And that's a good place. That's where you find all the candy. Side dishes, and then some little power bars just in case. So we have all this type of food. Some of it is dehydrated, and so we have to hydrate it, fill it up with water. Some of it is already made, and then all we have to do is heat it up. So something like this, I'm pulling out barbecued beef brisket. Pretty yummy. Not only is this food made in the US, but we also have food here from Japan. We've got Russian food. As you can see, all these red containers are filled with food that's from Russia. And then we get some of our specialty stuff, some things that we like, some of our favorite stuff that your family can send up. In fact, I like fluffernutters, and so I got sent up some fluff so I could make my fluffernutter with peanut butter. So you have a lot of food up here, no problems.
So here we are seeing that Sunita Williams is walking, not flying freely there around the International Space Station. But it is very difficult that is, thorough training is required for staying in zero gravity, because our body is designed with the functions of our body is designed based on gravity only. So we are taking food, and it is going to our stomach, and it is and the waste is going out of the stomach. All are based on gravity. So when it is going to that zero gravity, we will as if like ulta standing there. So our all systems, our digestive system, our heartbeat system, everything is disturbed. So we have to get thorough training to live in that zero gravity. The training means that first time when they are breaching there, they are full of vomiting is happening. If you are taking any food, it will vomit, because we are standing ulta in this space station, and our stomach and our lungs is having in between one diaphragm is there. So while we are standing ulta, this stomach will give force to our diaphragm, so we cannot take deep breath there in space station or in zero gravity. And the heart pumping is also different. So that it is against the gravity. So I think for 1 or 2 weeks they are having food full of headache because of this pumping irregularity. So all systems have to be trained well before coming to the space station. So very critical training. They have to rotate in that centrifuge and all. And another thing is the loneliness. We should have psychological strength, because we are staying away from a home. If you are closed in a room for 2 days or 3 days, you will get that loneliness feeling. So it has to be avoided. And here another thing is, every day you have to do some 3 hour 4 hour exercise, because in that zero gravity, while we are moving, our muscles are not working. So after some time, after some days, what happened? Since our muscle is having no exercise or no work, it forgets to move. So we have to strengthen the muscles every day. So some 3 or 4 hours per day we have to do exercise to strengthen our muscles. But how will we do exercise if we are taking some weight? There is no use. But there are spring loaded cycles, and that spring loaded things are there. So that way they have to do these exercises. So all and our medical parameters, body parameters should be well within the balanced condition. So all these things, it requires immense training for, I think, some 6 or 1 year immense training to stay in the space station. So now that you may be aware that Sunita Williams is now in space station, and she have to be brought back by April or May, something like that. And if they want to do the conditions inside the space station is maintained as like our Earth conditions. So if they want to go out of the space station for space walking and all, they have to wear the dresses, that is space suit. So and they have to be tied with the strongly with the space station. If there is any somehow if that rope breaks, or then they cannot come back to space station. So these type of difficulties are there for living in the zero gravities. And this is my last slide. See, you can see a pale blue dot. This is when Voyager 1 spacecraft to sent to Saturn. So it goes beyond Venus, then it turn back and take the photo of the Earth. So this is the Earth we are seeing in this world. So how much tiny our Earth we can see. So now I am stopping this. So if you have any doubts, you can ask. So if you don't have any doubts, we can wind up our session.
Hello.
Hello.
Is it audible? Hello.
Yeah, yes, sure.
I'm Kalishwaran.
Yeah.
So, do we build a propulsion system, electric arc propulsion system? Do we have ISRO or build a electric arc propulsion system? There is a indigenous cryogenic system we have.
Yeah.
But do we build electric arc propulsion system, or in the future is there a scope?
Yeah, I think some researches are going on. I think some proto model they have made electric propulsion system, but it is not yet come finalized. Still testing are going on.
Thank you.
Thank you, sir. On behalf of Marthandam College of Engineering and Technology, I would like to express my sincere gratitude to Shri Shaji Simon, Division Head, IISU VSSC Trivandrum, for the insightful and enriching session. Sir, your knowledge, insights, and passion have genuinely motivated and educated us. We appreciate the time and effort on sharing the valuable information. With your valuable presence, we had a wonderful session with a glimpse into the vast and infinite landscapes of thought. Now, I thank all the participants who attended this session. Let us eagerly wait for the upcoming sessions. Once again, I thank you all. Thank you.
Thank you, sir. Thank you.